but we have to kind of move into a different direction. We're going to do a thing called a development, which is right, the text starts on page 735 and moves basically through the end of the chapter. We're only going to cover the first couple pages of this because the rest of it is all examples on how to do different shapes and different techniques. And then if you come across one of these shapes, then you go into the text and look at those examples and extrapolate to what you need. So the first thing we probably ought to do is define a development. Okay, what is a development? The author's pretty much got it in the first sentence of this section, so I'll just read it verbatim. A development is the unfolded or unrolled flat or plane figure of a 3D object. So keep in mind, what we're use developments for is when we have a three-dimensional object that is hollow, okay, they're generally always hollow, then we can unfold them just like the glass box, put them on a single pattern or piece of paper or cardboard or sheet metal or whatever the case might be. We can cut these shapes out and then fold them back into the 3D shape. Now this works great, like I said, again, on hollow items. And we have a lot of hollow items out there. Think of right now, I can kind of hear one of the items that developments was used to create going on. Can you hear the AC on or the heater on? Ductwork. Real common development. Anytime we're moving fluids, air, many times rock, we used to pump rock, all things, but we need to move material. We generally do it through pipes or conveyors, things of this nature, and almost all of those are done using developments. Now, when we do developments, we have several different methods. They are shown here on this figure at the bottom of page 736 or 35. 35. Okay. So let's look at, let's look at the types. So you really have four types here. And the projection techniques that you use with these are slightly different, although there's many things in common before them. We have first what we call a parallel line development. And you're given two examples right here. Okay. Now again, keep in mind that these things are hollow. They are not consistent all the way through. When we call parallel line development, we develop the parallel lines of where we bend this object, and therefore that's where it gets its name. Okay. But we use this a lot of time on prisms or rectangles of any type, because we can then go ahead and measure a side and say, okay, we'll take that, bend it, and that'll come out here, a lot like the glass box does. Also, whenever we get cylinder type of work, that is generally done in a parallel line development also. And you'll see this when you do these, is that when you create the pattern or the shape that you are going to cut out, that's called a pattern, all the lines on it will be parallel to each other, parallel or perpendicular, and then you're doing a parallel line development. These are all generated, by the way, off of multi-views. Okay? So the steps are here, first you do the multi-view, and then you build the pattern or unfold the object based off of your multi-views, and you can project everything off of that. Okay. If you're not doing these two types, they do have a radial line development, and this is used for, well, the parallel line is far and away probably the most widely used one, because it just, we get that circle and we get that prism, and if you look at any ductwork or things at medium that we move objects through, they're almost always square or circular. Okay. Now, other times we do get other shapes like hoppers or tanks or canisters, things of that nature. Then we go to a radial line development. Now, the only thing different than this, again, you still need your multi-views, is all of your lines, your cut lines, your bend lines, everything come from a single point. Okay? And that's in essence what they're showing here. You can kind of see that the point of this cone or pyramid, everything comes to that point. Okay? And then you can go ahead and develop it from there. They show you another one down here that's a cone. So again, whenever you have something that goes to a vertex, you're going to be using radial line development. Now, you do have two others down here. I've never done this type, an approximate. I've just read on it. This is when we get spherical surfaces. Probably not in today's world, but I know in my world that I grew up in, we used to always get atlases. And they always had maps of the world. Do you remember those? Yeah, I see some of you closer to my age say, yeah, I remember those. Does that look familiar to you? Right, when you see a map of the globe? Hey, that's the exact same thing. It's a development of the earth. Now, certainly we can do this for other things. I mean, any of you go to the nightlife and you go to discos? We don't even have discos anymore or dance places.
We don't call them discos anymore.
Hey, what do you think they make all them lights and stuff out of up there? If it's not glass blown, it's done this way. And we can certainly do all of that type of work. Triangulation development is what we would use for regular polygons. Okay, because we can basically break things into triangles or hexagons or octagons, these sides, and we can then project those and fold them together. Okay, so those are the type of developments. I have two of them up here for you, and I'll pass them around just so you can kind of see them. So here I have a prism that was used with parallel line development. You can kind of look inside and see what's going on with this guy. So it's basically a prism. This came on a piece of paper and then folded up, and it was all calced on the computer. Here's another one, which is a truncated cylinder. Okay. Now this one has to have an auxiliary view that goes with it because we do have true size surfaces on it, such as that and the bottom. Okay. And on this one, again, you'll see all the fold lines on it. This was a parallel line development. And then I've got this one here, which is a little more complex. This one goes from a square to a circle. It's a transition piece, and it's a radial line development, and all the bend lines are on the inside. Okay, so we'll kind of pass these around so you can just take a look at them. They do work. They're actually a lot of fun. I have a hoot doing these things, and I think you probably will too. But it's kind of nice to calc all this out and then put it on a piece of paper and then cut it out and then you can fold it up and you can really see it, as opposed to a lot of work we do where it's really kind of abstract, right? When you're doing these objects, you have no idea what they're used for. Items like that.
So what you're saying is,
Go ahead, Cheryl.
is that you do a 3D an orthographic and an auxiliary if needed, and then also you put one of these on the drawing.
Actually, your construction people only need the pattern. They don't need the multi-view on this. They need what you are seeing right here.
Wait, is this would this be the multi-view? This?
No, that is what's
Right.
called a pattern. So
That's what the
if you
pattern
take
is.
this, okay, this has just got little pieces of tape on it, so you're welcome to come in here, and I'll just loosen them for you right here. It's a piece of paper, okay, that's flat. And then you just fold it up into the shape machine.
But so, to give that, then where would that be on the, what you're giving someone? To draw, I mean, to design?
You give them that pattern.
It would
And
be-
and they lay it out on a piece of sheet metal
So
or
this would
cardboard
be-
or whatever we're making it out of.
So would you have you'd have the prism and then you'd have this laid out? in multi-
Just that? That's all
Just
they
this,
need.
That's
not-
all you need.
Not the final,
That is all they need.
okay. So this is your pattern, you just call it pattern, it's not a multi, it's a pattern.
Yes, and that's all they
Okay,
need.
I can do that, okay, I got that, it's a pattern.
That's all they need.
Just a pattern.
We did the square round in my first year of welding.
Yeah.
Yeah, the layout.
Actually,
to have-
you've been on the receiving end of these, haven't you?
Yeah.
One thing, because we didn't do a lot of this in mining, because all our stuff was pretty much pre-bought and when we were doing our mills. But if you have some welding, then you may have to produce another drawing or your multi-views to go with it. Did you see those ends of them?
Well, what we got was that sheet that kind of shows you how to lay it out.
Mm-hmm.
There's that sheet that you gave me, and then we had to build, because you have to build 2 halves of them, right?
Yeah, many
Yeah.
times.
Yeah, you have to build 2 of the halves, and then bend them and put them together.
Okay. The only thing is we'll get into later on how we connect these things up. And we may have to give multi-views just for that, on how to join them all together. Okay. Anyway, these are your 4 types right here. And then you'll notice they go with really our 3D primitives, right? Okay, so you want to correlate that all the way back to drafting 131 when we talk about pyramids, cones, cylinders, truncated, right? Right truncated, whatever the case might be, then that would give you the method you're going to use and go ahead and draw it up. Now, when you do these, let's kind of move to page 737 and let's talk about the line types that are involved. Okay, here they have a pyramid. When we do these, you have, in essence, 2 line types involved. You have an object line, which you see around the outside here. Okay. Your object line is your cut line. Okay, so we use an OBJ for that. That's telling the person, this is where you will cut the material we are going to put together. Then you have a hidden line. That's right in here. A hidden lines will always be interior to a pattern. They tell you where you are bending the item. This is where we're going to put it. If it's a small little piece, we might be able to bend it by hand, like a ductwork. Maybe it's a big thing, like a tank that's going into the ground for all these convenience stores that got gas pumps. Okay, those are done through developments. And that might be 1-inch plate steel. Okay, then you're going to need a pretty big machine to do the bending for you, but you still bend it the same way. Okay. Now the last part you got is that connection thing I just mentioned ago, which we call a seam. And you see it right here, here, and here. And these are how, when we fold them up, it's excess material that will go inside of the object or outside of it, and then we can spot weld it, we can tape it, we can glue it, whatever the case might be, depending on where it's at. And there's some pretty big markets out there for this stuff, folks. We got an engineering firm in town, McClure Engineering, that does a ton of this work. And they work for most of the food processing places around here on all of their plants and things of that nature that are doing those types of work. We also have a company that makes their living on this. It does all the McDonald's boxes. I think Burger King is also their client. So whenever you go and stop at these fast food places and they give you that hamburger in that box, it's probably made here in Twin Falls. And it's a development drawing. And they knock them out here. So in essence, those are your 3 line types. OBJ's a cut, hidden's a fold, and then you may have to have seams or connection devices that go with it. You see a bunch of the folds down below. We can put them together like this, where we're just locking them together. This is mostly real thin material, of course, okay, where they bend it in little clip type shapes, and then we can slide the stuff together like you see an E, a grooved seam, or a double seam, and we can connect them all up. And also, one other thing you'll see, these edges get pretty flimsy if you're using a thin material. So a lot of times they'll fold over these edges just to give that edge a little bit of strength. Okay. So when you're moving it, it stays its shape. And steel actually gets quite a bit stronger the more you bend it, because we start resisting different directions. Following that, you just have a bunch of examples. Okay? So page 738, here's an example on a truncated prism and how you would do it. Notice that as they come through, we're starting with what? Top front. Okay. Now this one's going to actually require an auxiliary view because we have an inclined plane in it. You're going to see that inclined plane. It shows up. They don't give it to you in the text. That's it right there. Okay. That's that inclined plane. It's the top of the object. Now the main fold out when you do these, you use what's called a stretch out line. This is a parallel line development. So we do a stretch out line, which is this line here. Now this is the distance all the way around this guy. Okay, so that's where you get that distance from. Okay. So if I go from 1 to 2, that's that distance. 2 to 3 is that distance. 3 to 4 is that distance. And then back to 4 to 1 is that one. Now that takes care of all your sides. If you are going to put a bottom on it, then you need to attach that. If you're going to put a top on it, you need to attach that. You can put them wherever you want as a general rule. Here, you see the bottom attached right here with a couple seams? Okay. Now, when you fold this up, this will then hinge and go underneath. But this bottom, what we want to do is maximize the material we're working with. So when we do this, we're probably on a 4x8 sheet or something like that. We want to make a bunch of these things, right? And organize them as well as we can so we don't waste it. This bottom may go here. It could also go right here on this piece, and it would work just as well. We've got to kind of look at that stuff. I can also take this bottom, I can rotate it 90 degrees and put it right there. That would also work. In essence, we do have some variables that allow us to not waste material. Now, when you do this auxiliary view, it's only got 2 places it can go. Okay? It can only go here or here, either or. That's the only place it would fold up correctly. Well, that's not necessarily true, is it?
You can
Four
draw it
and
on 2
one,
and 3,
row
put it this way. Put it on 2 and 3.
I don't know. Could we put it on 2 to 3?
It's the same, you know.
I don't know that we could.
Who's gonna fall down?
I'd have to draw it.
Anyway.
Well, no, it's got to fold in the right direction. Okay, 'cause if I moved it up here,
It's gonna fold over, and the other has to fold
it's
too.
going to fold that way though.
Just coffee.
No, it's not going to work. It's got to be there or between 1 and 2.
What about 4 and 1?
Oh, yeah.
You might be able to have it on 4 and 1 and then fold it over the top.
Yeah.
Yeah, you might be able to. I'd have to look at it a little closer. The point really is that you do have options where you can move that stuff. Page 739, here they've got cylinders and examples of how to lay them out. When you get these curved surfaces, notice on this one, I'll look at this example right here. Again, how are they starting? We're starting with a front and top view. Okay, again, parallel line development, this stretch out line right here is equal to the circumference. And then we go ahead and lay out our fold lines. In this case, they chose 13 or 12, looks like. I'm not sure what they got going here. And then we use projection when we have these warped surfaces that are created by truncated shapes. So you can kind of see how they're creating that on the stretch out line based on my multi-views. Because I've got to come from them multi-views. I've got to come from true length surfaces. Because that's in essence what I'm doing, is taking these true lengths and placing them on paper. Again, on this one, since it is truncated, needs an auxiliary view. There it is. There's your inclined plane, true size and shape. There's the bottom. This one might look pretty familiar to one of the ones I'm passing around. So, in essence, you just keep going for all different types. Now, your text is not all inclusive, but it does have a lot of pretty tough ones that are given to you. They show you radial line development for this oblique cone on page 742. Now, these true lengths here, again, are basically using the laws of descriptive geometry to define them. And I'm not going to take the time to go through every one of these steps. Okay, but this would be a radial line development. You can see how all the cut and bend lines here come from a single vertex. We still, since it's truncated, you still have these kind of obtuse or irregular curves, might be a better way to place it, to get that warped surface to turn up. And then this keeps going. You do have one piece, figure 1540 on 745. This one might look a little familiar to you. It's exactly how I did it. This is that other piece that I was passing around. A transition piece that goes from a square to a circle over a distance. So a case where we might go from square ducting to circular ducting or storage material, whatever. When you do these, I kind of wrote down the steps here for you. When you do them, here's basically what you're going to do. First, develop your multi-views of your object. This will usually be at least a 2-view drawing. Depending on the complexity of the object, you may have to do more. If it's a truncated device, by truncated located, it's going to be cut, right, on some angle. You're going to get an inclined or an oblique plane. So therefore, you may have to produce your auxiliary views of these surfaces. After you do that, you basically do your stretch outlines. You want to do a datum, or set yourself, remember we use the reference plane method on auxiliary views to transfer measurements? In essence, you need to do the same thing here. You're going to find a common point on the object that is solid, and you can transfer measurements from it. After you've got that pattern done, we're going to locate our folds. How do we want to bend it? If it doesn't have to be a perfect circle or something, maybe I only bend like a circular piece 4 times and it's kind of prism-like looking. Still performs okay. Maybe I got to bend the thing 50 times to get the shape that's desired. Depends on the object. Then you add your tops and bottoms. Once you finish the main pattern, again here this is probably just copying right from your multi-views, because your tops and bottoms need to be true size and shape that you add on here. Last thing you will do is add any seams. Now, one thing to add on seams. When we bend material, it doesn't stay the same shape. Or I guess that's the wrong thing to say. Of course, we're bending it, it's not the same shape. It doesn't stay the same size. Okay? Let me try and illustrate this. So if I take an object like this, and I decide I'm going to bend it. Okay? So I grab the thing and I bend it. What happens to the side on this side right here?
It compresses.
What happens to it?
To which side?
This side of the material, just this side. Just think of this.
Squished together.
It's getting squished together, right? Okay, because it's under a compressive force. What happens to the top of it?
Stretched out.
It's getting stretched. Very rarely do the bottoms and tops move exactly the same. Okay? The thing is when you bend it, it's going to stretch more than it's going to compress. And so you'll take an object that, let's say it's 2 inches long and you fold it in half, it's not going to fold up to 1 inch. It's not. You'll lose a little bit due to the fact that it's going to compress more material than it's going to stretch it out. The general rule is that you add half the material thickness for every bend that you do. Now, we're not going to do that for right here. This is for somebody who is doing it and this is all they do and they need a high degree of precision. Okay, many times we don't need this degree of precision where we start adding in the shrinkage that occurs on a bend. Okay? But if you do, it's half the material thickness. That's a general rule. All material moves differently. You could do a quick internet search on this and probably get any type of alloy or whatever, and it would tell you what the stretches are for the angle of bend that occurs. Okay? And then you would add that. Now, when you get this, if you do have to go to this, and there's a company in town, Trans-System, do you know them big green trucks running around hauling all the sugar beets? Well, they build them here, and they use a lot of developments for those tanks. When they do it, they actually do take this into account because they've got to get to an exact tonnage that those trucks are rated for. So,
Question.
yes.
When you're doing a regular prism, you want it to be round, or something like that, or cone. Is there a standard, how many lines you should have in the development? If you want it to be smooth, it should be every half, I mean, is there a standard?
No, not really. It's trial and error. I mean,
Okay.
once you've done a few, then you know
Okay.
what you need to do.
Okay.
You know, like that, the transition piece I passed around that went from the square to the round.
Yeah.
I originally did that at 4 on every corner,
Mhm.
and I hated the shape. And so I went back and added another 4 to every corner. And now I started seeing the rounding occur. It's going to mesh better with the mating device. Okay, so it's kind of trial and error. Now, people with experience that do this all the time, yeah, they tell you, oh, you have to bend that many times, bend that, you know, they've done it, right? For us, it's trial and error. We don't do it every single day.
Okay, and then the fold extra piece, that's your discretion also.
The seam, you mean?
The seam, you'll have far to go from the seam.
Depends on what they need and what you're doing
So
for it.
that's,
Yeah, if I'm gluing it, you know, they don't need to be very big. If I need to weld it, I might need enough material I can get in there and do a weld with and clamp it. And, you know, there's a lot of different ways to join those devices.
and who gives you that information? I mean, like you determine that, or is the designer gonna tell you? I mean-
Team effort,
Okay,
team effort. There might be an engineer involved, there might be a machinist involved, there might be a welder fabricator, there might be a couple drafters. Yeah, team. All right, so in essence, that's it. Any questions so far? Okay, I did hand you out this last sheet. No more for this class. Oh. The first two, G17 and G18, are required, and those will be graded. Please pay attention to the instructions. For most of these, I want the pattern and the folded up object. I do have an extra credit one down on the bottom. This guy's going to be worth 2 extra credit points if you want to do it. If you want to do it, G19, let me know, because I'm going to let you try it on your own for 1 day, and then I've got a primer that I will hand you on how to do these that we put together, and you can check your work. But I'd like you to kind of struggle with it at least for 1 day, let it sit in your mind, and so that then you get it where somebody's saying, do this, do this, do this, then it starts to make sense. All right, with that said, I'm done as far as this goes. You will have no more new material for this section. We're going to do a test review tomorrow. Yes, Cheryl?
When are all the project drafting papers due?
As quick as possible. We will be starting drafting 134 on Tuesday.
all these are private.
I remembered. Tuesday, and you won't have an assignment for a couple days. So technically